Hey class, in today's lesson we're going to talk about exponential functions and their graphs, which is found in section 3.1 part 2. Our objectives are to recognize, evaluate, and graph exponential functions with base e, and to use exponential functions to model and solve real-life problems. So the graph that you see at the top of our page is the graph of the natural exponential function. Its domain is from negative infinity to positive infinity. The range is strictly from 0 to infinity, and it has a y-intercept at 0, 1. So many applications, the convenient choice for a base is the irrational number e, which is about 2.71828 with a whole lot of numbers after that. And this number that's not what that's supposed to say. This number is called, is what it's supposed to say. This number is called. So let me edit that. It's called the natural base. The function f of x equals e to the x is the natural exponential function. And so this chapter is going to focus a lot on the natural base and the natural exponential function. So as we move forward, just remember in mind that this is like the parent function that we're going to be focusing on, which is f of x equals e to the x power. All right, so in example 6, what we're going to do is we're going to evaluate with our calculator each expression that we see, and then we're going to round the result to the nearest thousandth. Okay, so if we found e, now by the way, e on your calculator is actually on the first column. You see a ln button near the number 4. To get the e, you have to press second and then the ln button. Okay, so anyways, e to the negative second is about 0.135. E to the negative first is about 0.368. E to the first is about what we said earlier, 2.718. And then the last one, e to the second, is about 7.389. Alrighty, let's keep going. With example 7, now we're going to sketch using a table. So again, at this point, really all we're doing is basic algebra 1. Okay, we're going to create a table using some fairly simple values of -2, -1, 0, 1, and 2. So if I tried to find this first value, I'd do 2e to the 0.24 times -2. Okay, that value is going to be about 1.238. Okay, if I did the same for the rest of these, I'd have about 1.573, and these aren't exact, they're just estimates. 2, then 2.532 or 542, and then 3.232. Okay, when we graph, we'll have -2 and 1.238, which is just a little bit above the 1. -1 and 1.5, so a little higher. 0 and 2, which is a little higher than that. 1 and 2.5, so just a little higher than that. And then 3 and 3.2 is a little over the 3. So this graph is essentially shaped like that. Okay, so this is just how we graph. And again, most of this is kind of like the Algebra 1 skill of knowing how to substitute and find outputs. Okay, we're going to do one similar to this that is a try. So for this table, again, we want to choose -2, -1, 0, 1, 2. Okay, these values are 1/2 e to the negative 0.58 times -2 power. This is going to be about 1.595. The next one is 0.893, then 0.5, 0.280, and then 0.157. Okay, when we graph, you will have -2 and 1.595, so just a little bit over 1.5. -1 and a little under 1. 0.5. 1 and 0.20, and then it just gets lower and lower. So this graph should look about that. Towards the end over here, you see that it is under the x-axis. That's not accurate. I just kind of moved my graph a little bit too low. Let's keep going. Compound interest. One of the most familiar examples of the exponential growth is that of an investment earning continuously compounded interest with principal P invested at an annual interest rate of R compounded at T years. So if you have a problem that talks about N compoundings per year, then you use our first formula. If you hear about something that's continuously compounded, so throughout the course of the year, that's pretty much like an everyday type situation, you would use the second function. So the first one is for compound function, the second one is for continuous compound. All right, so for example A, it says finding the balance for compound interest, and I'm going to switch colors to blue so we can see this a little bit on top of this. But it says a sum of $9,000 is invested at an annual interest rate of 8.5% compounded annually. Find the balance in the account after 3 years. So this one, because it's a compounded annual situation, we're going to use this formula, and even the blue is pretty bad. A equals P times 1 plus R over N to the NT power. Let's see if I switch it to black, if that'll be better. Okay, maybe a little bit. Okay, so with that, we need to know what capital P is. We need to find R, we need to find N, and we also need to find T. So based off this problem, P is the principal, and our principal is $9,000. That's how much we originally invested. R is the rate, so the rate is 8.5%. However, you need to write that as a decimal. And so as a decimal, if you knock off the percent and move the decimal 2 places to the left, it's about 0.085. N is, N is the amount of times per year that is compounded. So since it says annually, that means once a year. So N is 1. And then T is how many years? And so it's 3 years. So if we substitute all these numbers in, A is equal to 9,000 times 1 plus the rate 0.085 over 1 times, or to the 1 times 3 power. Okay, if I simplify that, or if you throw it in your calculator all at once, you can. It's going to give you about, and actually let me just show you one more step. That's 9,000 times 1.85 to the 3rd power. Okay, that's what everything would be simplified. It would be about $11,495.60. And since this is money, we should definitely show everything, including the change. Okay, let's look at our try number 8. It says a total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if it's compounded, A, if it's quarterly, and B, if it's continuously. Now, they gave you these 2 different instances because you will use 2 different formulas. Okay, for the quarterly, we'll use the same formula we just used, but if it is compounded continuously, we'll use the A equals P times E to the RT power. All right, so for part A, we will have A equal to P times 1 plus R over N to the NT power. All right, that P is 12,000 times 1 plus the R, which is the rate, is 0.09, because again, we knocked off our decimal and moved it 2 places to the left, over N. The amount of times it was compounded a year. Quarterly means 4 times a year, so it's going to be over 4 raised to the 4 times 5. 4 again for the N, 5 for the amount of years. If I throw that into my calculator all at once, it's going to be about $18,726.11. All right, part B. That formula is A equals P sub E to the RT. I should have said sub E, it's P times E. All right, anyways, you will get 12,000 times E to the R. R again is 0.09 times T is 5 years. If I throw that all into my calculator, I'll get about $18,819.75. Alrighty, let's look at our last problem. All right, so in example 10, we're talking about radioactive decay. So it says, let Y represent the mass of a quantity of a radioactive element whose half-life is 25 years. After T years, the mass in grams is Y equals 10 times 1/2 to the T over 25. What is the initial mass, and how much is the initial mass after is present, or excuse me, how much of the initial mass is present after 80 years? All right, so to find the initial mass, then that means that time is 0 years. So we, for the initial mass, would have Y equals 10 times 1/2 to the 0 times 25, okay? So 0 times 25 is 0. Anything to 0 power is 1, so this is really 10 times 1, which makes this 10 grams. Okay, so there's 10 grams for the first year. All right, if we, after 80 years, want to know how much is left, we would say Y equals 10 times 1/2 to the 80 times 25. Again, typing that all in, you get about 1.088 grams. So it is drastically dropped. However, there's still enough after 80 years to still make that radioactive. All right, guys, we are done with this lesson. If you have any questions, please be sure to come see me for tutoring.